Imagine standing in the most isolated place you can think of. Perhaps it's the middle of a vast desert, where the silence stretches endlessly in every direction, broken only by the whisper of wind across sand dunes. Or maybe it's deep within an ancient forest, where towering trees create a cathedral of solitude, and the only sounds are your own footsteps on fallen leaves. Now, take that feeling of profound isolation, that sense of being utterly alone in an immense space, and multiply it by a billion times. What you would experience then is something approaching the loneliness of a cosmic void. These are the loneliest places in the universe, regions of space so vast and empty that they dwarf our comprehension, stretching across hundreds of millions of light years, with almost nothing to break the cosmic silence. They are the great empty chambers of existence, the spaces between the stars and galaxies, where darkness reigns supreme and matter becomes so sparse that an observer might travel for eons without encountering a single point of light. To understand the profound nature of this emptiness, consider that our entire Milky Way galaxy, with its 400 billion stars, would be nothing more than a tiny speck of dust floating in these immense voids. The distance from one end of our galaxy to the other, a journey that light itself takes 100,000 years to complete, represents merely a fraction of a percent of the width of the largest cosmic voids. We are speaking of emptiness on a scale that challenges the very limits of human imagination. The story of how we discovered these cosmic deserts begins with a moment of scientific shock that forever changed our understanding of the universe. In 1981, astronomer Robert Kirshner was conducting what seemed like routine observations at the Kitt Peak National Observatory in Arizona. He was part of a team measuring the redshift of galaxies, essentially mapping their distances from Earth by analyzing how the expansion of the universe had stretched their light toward the red end of the spectrum. It was meticulous work, the kind that builds our cosmic senses one galaxy at a time. But as Kirshner and his colleagues plotted their measurements, something extraordinary and unsettling began to emerge from the data. In the direction of the constellation Boötes, there was almost nothing. Where they expected to find the usual scattering of galaxies that populate the cosmos, they found instead a region of space that was almost completely empty. The void they had stumbled upon was so large that it would later be dubbed the Great Nothing, a sphere of emptiness stretching 330 million light years across. This discovery sent shock waves through the astronomical community because it violated one of their most fundamental assumptions about the universe. Since the 1960s, scientists had been studying the cosmic microwave background radiation, the afterglow of the Big Bang that permeates all of space. This radiation is remarkably uniform, varying by only tiny fractions of a percent across the entire sky. From this uniformity, astronomers had reasonably concluded that matter in the universe should also be distributed fairly evenly. If you zoomed out far enough, they believed, the cosmos should look homogeneous, like a smooth soup of galaxies scattered randomly throughout space. The Boötes Void shattered this expectation. Here was a region containing only 60 galaxies, where astronomers would have expected to find 2,000. It was as if someone had scooped out a massive portion of the universe, leaving behind a hollow shell surrounded by walls of galaxies. The implications were staggering. If such enormous empty regions could exist, then the universe was not the uniform, predictable place they had imagined. Instead, it had structure on the largest scales imaginable, with matter organized into a vast cosmic web of filaments and walls surrounding these immense voids. As more surveys were conducted and technology improved, astronomers began to realize that the Boötes Void was not an anomaly. It was part of a fundamental architecture that governs the largest scales of cosmic structure. The universe, they discovered, resembles a vast three-dimensional spiderweb, with galaxies strung along thin filaments of dark matter that stretch across hundreds of millions of light years. Where these filaments intersect, matter clusters together to form the superclusters of galaxies that contain hundreds or thousands of individual galaxies, like our own Milky Way. But between these filaments lie the voids, enormous regions where matter is so sparse that they contain less than 15% of the average density of matter in the universe. To put this in perspective, imagine a block of Swiss cheese magnified to cosmic proportions. The cheese itself represents the filaments and walls where galaxies cluster together, while the holes represent the voids. But unlike the holes in cheese, which are merely empty space, cosmic voids are not completely empty. They contain dark matter, the invisible substance that makes up most of the matter in the universe, as well as a sparse population of galaxies that formed in these low-density environments. These void galaxies are different from their counterparts in denser regions of space. They tend to be smaller, bluer, and more isolated, having formed in environments where the raw materials for star formation are scarce, and the gravitational influences of neighboring galaxies are minimal. They are the hermits of the cosmic community, existing in splendid isolation within the vast empty chambers of space. The discovery of cosmic voids has revolutionized our understanding of how the universe evolved from the smooth, uniform state revealed by the cosmic microwave background to the highly structured cosmos we observe today. The story begins in the first moments after the Big Bang, when quantum fluctuations in the primordial universe created tiny variations in density. These fluctuations were incredibly small, differing from the average density by only 1 part in 100,000. Yet over the course of billions of years, gravity amplified these minute differences into the grand architecture we see today. Regions that were slightly denser than average attracted more matter through gravitational attraction, growing ever denser and eventually forming the filaments and walls of the cosmic web. Meanwhile, regions that were slightly less dense than average had their matter gradually drained away by the gravitational pull of their denser neighbors. Over cosmic time, these underdense regions expanded and merged, forming the vast voids that now dominate the volume of the universe. Today we know that approximately 80% of the universe's volume consists of these cosmic voids. We live not in a universe filled with matter, but in a universe where emptiness is the dominant feature and matter is confined to thin filaments and walls that surround immense regions of near-nothingness. This realization has profound implications for our understanding of cosmic evolution. the nature of dark matter and dark energy, and even the fundamental laws of physics themselves. The voids are not merely empty spaces to be catalogued and forgotten. They are active participants in the cosmic drama, expanding faster than the denser regions of the universe due to their low matter content and the influence of dark energy. They serve as natural laboratories where we can test our theories of gravity on the largest scales, study the properties of dark matter and dark energy, and even probe the masses of neutrinos, those ghostly particles that pervade the universe while barely interacting with ordinary matter. As we prepare to journey deeper into these cosmic deserts, to explore their hidden secrets and contemplate their profound implications for our understanding of existence itself, we must remember that we are embarking on a voyage into the most fundamental aspects of reality. The voids are not simply empty spaces between the interesting parts of the universe. They are integral to the cosmic story, holding clues to the deepest mysteries of physics and cosmology. In the vast silence of these cosmic chambers, where light from distant galaxies takes hundreds of millions of years to cross from one side to the other, we find not just emptiness, but a different kind of fullness, a fullness of possibility, of mystery, and of the profound questions that drive us to explore the furthest reaches of space and time. Let us now venture into this great cosmic silence to discover what the loneliest places in the universe can teach us about the nature of existence itself. The transformation of our understanding of cosmic structure represents one of the most profound shifts in astronomical thinking, since Copernicus displaced Earth from the center of the universe. For centuries, astronomers gazed upward at a two-dimensional tapestry of stars scattered across the night sky, unable to perceive the true three-dimensional architecture that governs the largest scales of existence. The breakthrough came not through a single moment of revelation, but through the painstaking accumulation of distance measurements that gradually revealed the universe's hidden geometry. In the early decades of the 20th century, astronomers like Edwin Hubble were making the first systematic measurements of galaxy distances, discovering that these island universes were far more distant than anyone had imagined. But even as they mapped the positions of thousands of galaxies, the true structure of the cosmic web remained hidden. The galaxies appeared to be scattered randomly across space, like stars in the night sky, with no obvious pattern or organization beyond the tendency to cluster together in small groups. The revolution began in the 1970s with the development of large-scale redshift surveys. By measuring the redshift of galaxy light, astronomers could determine not just the direction to each galaxy, but also its distance from Earth. For the first time, they could create true three-dimensional maps of the universe, revealing the spatial relationships between galaxies separated by hundreds of millions of light years. What they discovered fundamentally altered our conception of cosmic architecture. The universe, they found, is not a random scattering of galaxies, but a vast three-dimensional web of matter and emptiness. Imagine taking a bar of soap and whipping it into a rich foam, creating bubbles of various sizes surrounded by thin films of soapy water. Now imagine that this foam has been stretched and expanded, until each bubble is hundreds of millions of light years across, and the soap films have become walls and filaments of galaxies. This is the cosmic web, the largest scale structure in the universe, and it governs the distribution of matter on scales so vast that our entire local group of galaxies occupies merely a tiny corner of a single filament. The cosmic web consists of 4 primary components, each playing a crucial role in the grand architecture of space. The most dramatic and voluminous components are the voids themselves, vast, roughly spherical regions where the density of matter drops to a small fraction of the cosmic average. These voids typically span tens to hundreds of millions of light years and contain so few galaxies that an observer placed within one might see only empty darkness in every direction, with the nearest neighboring galaxy clusters appearing as faint smudges of light on the distant horizon. Surrounding these voids are the walls, sheet-like structures where matter density approaches the cosmic average. These walls are not solid barriers, but rather regions where galaxies are distributed in roughly planar arrangements, creating vast surfaces that separate one void from another. The walls themselves are not uniform, but contain substructure in the form of filaments and clusters that give them a complex, web-like appearance when viewed on smaller scales. The filaments represent the backbone of the cosmic web, thread-like structures where matter has been compressed by gravitational forces into linear arrangements that can stretch for hundreds of millions of light years. These filaments serve as the highways of the universe, channels along which matter flows and where most galaxies form and evolve. Our own Milky Way galaxy lies within such a filament, part of a structure that connects our local group to the massive Virgo cluster and extends far beyond into the depths of space. Where multiple filaments intersect, matter accumulates into clusters and superclusters, the densest regions of the cosmic web. These are the great cities of the universe, containing thousands of galaxies, bound together by gravity into structures that can span tens of millions of light years. The largest of these superclusters, such as the Shapley supercluster, contain the mass of tens of thousands of Milky Way galaxies and represent the most massive gravitationally bound structures in the universe. But it is the voids that dominate the cosmic landscape, not through their mass, but through their sheer volume. While the filaments and walls contain most of the universe's matter, the voids contain most of its space. Recent surveys suggest that voids occupy approximately 80% of the universe's volume, making emptiness the dominant feature of cosmic architecture. This realization has profound implications for our understanding of cosmic evolution and the fundamental forces that shape the universe. The boundaries of cosmic voids are not sharp edges like the walls of a room, but rather gradual transitions where the density of matter slowly increases from the sparse interior toward the denser walls and filaments. Within the deepest parts of a void, the density of matter may drop to as low as 10% of the cosmic average, creating regions where galaxies are separated by distances so vast that light from one galaxy would take tens of millions of years to reach its nearest neighbor. Yet even in these seemingly empty regions, the universe is far from devoid of structure. Dark matter, the invisible substance that comprises most of the matter in the universe, forms a subtle web of gravitational influence that permeates even the emptiest voids. This dark matter scaffolding, though sparse, provides the framework upon which the few void galaxies that do exist have formed and evolved. Computer simulations reveal that even in the deepest voids, dark matter forms a delicate network of filaments and halos, invisible to our telescopes, but crucial to understanding the dynamics of these seemingly empty regions. The discovery of this cosmic architecture has revolutionized our understanding of how structure forms and evolves in the universe. The traditional picture of galaxy formation, in which galaxies condensed out of a uniform primordial medium, like raindrops forming in a cloud, has been replaced by a more complex narrative in which the cosmic web itself plays a fundamental role in determining where and how galaxies form. Galaxies that form within the dense filaments of the cosmic web have access to abundant supplies of gas and dark matter, allowing them to grow large and bright through sustained star formation. These galaxies often interact and merge with their neighbors, creating the massive elliptical galaxies and rich clusters that dominate the dense regions of the universe. In contrast, galaxies that form within the sparse environment of cosmic voids face a much more challenging existence, with limited access to the raw materials needed for star formation and growth. The cosmic web also influences the flow of matter on the largest scales, creating vast streams and currents that transport gas and dark matter from the voids toward the filaments and clusters. These flows, invisible to direct observation but revealed through computer simulations, represent some of the largest coherent motions in the universe, with matter streaming along filaments at velocities of hundreds of kilometers per second across distances of hundreds of millions of light years. Understanding the cosmic web has also provided crucial insights into the nature of dark energy, the mysterious force that is accelerating the expansion of the universe. Because voids contain relatively little matter, they are dominated by dark energy, making them natural laboratories for studying this enigmatic component of the cosmos. The expansion rate of voids provides a direct probe of dark energy's properties, and observations of void evolution over cosmic time may hold the key to understanding whether dark energy is truly constant, or whether its strength has changed over the history of the universe. The study of cosmic voids has also revealed unexpected connections between the largest and smallest scales in physics. The same quantum fluctuations that gave rise to the cosmic web also left their imprint on the cosmic microwave background radiation, the afterglow of the Big Bang. By comparing the statistical properties of voids with the patterns observed in the cosmic microwave background, astronomers can test our understanding of the early universe and the fundamental physics that govern the first moments after the Big Bang. As we continue our journey into the cosmic web, we must remember that we are not merely passive observers of this grand architecture, but active participants within it. Our galaxy, our solar system, and our planet exist within the cosmic web, shaped by the same forces that created the vast voids and towering filaments that surround us. The matter that makes up our bodies was forged in stars that formed within this web, and the very atoms we are made of have journeyed across cosmic time and space, flowing along the filaments and through the voids that define the largest scale structure of the universe. The cosmic web represents more than just a description of how matter is distributed in space. It is a testament to the power of gravity to create order from chaos, to build complex structures from simple initial conditions, and to connect the smallest quantum fluctuations with the largest structures in the observable universe. In the architecture of emptiness, we find not just a map of where matter is and is not, but a guide to understanding the fundamental forces and processes that have shaped the cosmos from its earliest moments to the present day. Among the countless voids that populate the cosmic web, a few stand out as monuments to the power of emptiness, regions so vast and barren that they challenge our understanding of how such structures could have formed in a universe that began in a state of near perfect uniformity. These are the supervoids, the largest and most dramatic examples of cosmic emptiness, each with its own story of discovery and its own implications for our understanding of the universe. The most famous of these cosmic deserts is the Boötes Void, the region that Robert Kirshner and his colleagues stumbled upon in their 1981 survey, and which earned the colloquial name the Great Nothing. To truly appreciate the scale of this emptiness, we must journey back to that moment of discovery and understand the profound shock it delivered to the astronomical community. Kirshner's team was conducting what they thought would be a routine mapping of galaxy redshifts in the direction of the constellation Boötes. They expected to find the usual distribution of galaxies scattered throughout space, perhaps with some clustering here and there, but nothing that would fundamentally challenge their understanding of cosmic structure. Instead, as they plotted each galaxy's position in three-dimensional space, a vast empty region began to emerge from their data like a hole in the fabric of the universe itself. The Boötes Void stretches across a diameter of 330 million light-years, making it one of the largest known structures in the universe. To put this scale in perspective, consider that light from one side of this void takes 330 million years to reach the other side, traveling at the fastest speed possible in our universe. During that journey, light would pass through a region containing only 60 galaxies, scattered like lonely islands in an ocean of darkness. In a typical region of space this size, astronomers would expect to find approximately 2,000 galaxies, making the Boötes Void more than 30 times emptier than the cosmic average. The center of this great emptiness lies 700 million light-years from Earth, positioned at coordinates that place it in the direction of the constellation Boötes, as seen from our perspective. But the void itself is not a two-dimensional feature projected against the sky, but a three-dimensional bubble of near nothingness that extends deep into space. An observer placed at the center of the Boötes Void would see a night sky almost completely devoid of galaxies, with only the faintest smudges of light marking the distant walls where normal cosmic structure resumes. The few galaxies that do exist within the Boötes Void are themselves unusual, bearing the characteristics of objects that formed and evolved in isolation. They tend to be smaller and bluer than typical galaxies, with active star formation that suggests they have had different evolutionary histories than their counterparts in denser regions of space. These void galaxies represent natural experiments in galaxy formation, showing us how cosmic structures develop when freed from the gravitational influences and interactions that shape most galactic evolution. The discovery of the Boötes Void raised immediate questions about how such a structure could have formed. The standard model of cosmic evolution, based on the growth of small density fluctuations through gravitational instability, seemed inadequate to explain such a vast region of emptiness. Computer simulations suggested that the void likely formed through the coalescence of smaller voids, a process in which multiple underdense regions merged over cosmic time to create the single large structure we observe today. This coalescence process provides a window into the early universe, when the cosmic web was still taking shape. In the first billion years after the Big Bang, the universe contained many small voids and overdense regions, distributed according to the pattern of quantum fluctuations that emerged from cosmic inflation. Over time, gravity caused matter to flow from the underdense regions toward the overdense ones, gradually emptying the voids while building up the filaments and walls. The largest voids, like Boötes, represent regions where this process was particularly efficient, creating vast reservoirs of emptiness that continue to expand as the universe ages. But the Boötes Void, remarkable as it is, may not even be the largest void in our cosmic neighborhood. In recent years, astronomers have identified an even more extraordinary structure, one that may fundamentally challenge our understanding of cosmic homogeneity and the basic assumptions underlying modern cosmology. This is the KBC Void, named after the astronomers Ryan Keenan, Amy Barger, and Lennox Cowie, who first proposed its existence, and it presents the startling possibility that we ourselves live within a cosmic supervoid. The KBC Void, also known as the local hole, is a structure of almost incomprehensible scale, stretching approximately 2 billion light-years across, and encompassing not just our Milky Way galaxy, but our entire local group, the Virgo cluster, and much of the larger Laniakea supercluster of which we are a part. If this structure truly is a void in the conventional sense, then we are living within one of the largest known underdensities in the observable universe, surrounded by a vast region where the density of matter is significantly below the cosmic average. The implications of residing within such a structure are profound and potentially revolutionary. For decades, cosmologists have relied on the assumption that our location in the universe is typical, that we observe the cosmos from a representative vantage point that allows us to make general statements about cosmic properties and evolution. This assumption, known as the Copernican principle, has been fundamental to the development of modern cosmology and underlies many of our most important conclusions about the nature of dark energy and the expansion of the universe. If we live within the KBC Void, however, our observations of cosmic expansion may be biased by our unusual location. Matter within a void expands faster than the cosmic average due to the reduced gravitational pull from surrounding material, potentially creating the illusion of accelerated expansion that we attribute to dark energy. Some researchers have suggested that the apparent acceleration of cosmic expansion, one of the most important discoveries in modern astronomy, might be explained not by a mysterious dark energy that permeates all of space, but by our residence within a vast underdense region. This possibility has sparked intense debate within the cosmological community. The existence of such a large void would challenge the cosmological principle, the assumption that the universe is homogeneous and isotropic on large scales. Structures as large as the proposed KBC Void push against the limits of what current theories of cosmic evolution can easily explain, requiring either modifications to our understanding of structure formation or acceptance that the universe may be less homogeneous than we have assumed. The evidence for the KBC Void comes from multiple independent observations. Studies of the cosmic microwave background radiation have identified what appears to be a cold spot that could be the signature of a large underdensity in the direction of our local group. Measurements of the local expansion rate of the universe, known as the Hubble constant, consistently yield values that differ from those inferred from observations of the early universe, a discrepancy known as the Hubble tension that could be explained by our location within a void. Additionally, observations of type Ia supernovae, the standard candles used to measure cosmic distances and discover the acceleration of the universe, show subtle patterns that could be consistent with our residence within a large underdense region. While none of these observations definitively proves the existence of the KBC Void, taken together, they paint a picture of a universe that may be more structured and less homogeneous than the standard cosmological model assumes. The third great void that has captured astronomical attention is the Eridanus supervoid, a massive underdensity located 1.8 billion light-years away in the direction of the constellation Eridanus. This structure is notable not just for its size, but for its connection to one of the most puzzling features observed in the cosmic microwave background radiation: the cold spot. The cold spot is a region of the cosmic microwave background that appears significantly colder than the surrounding areas, creating what looks like a hole in the otherwise uniform afterglow of the Big Bang. When this feature was first discovered in data from the Wilkinson Microwave Anisotropy Probe, it created considerable excitement and concern among cosmologists. The spot was so large and so cold that it seemed to violate the statistical expectations for fluctuations in the cosmic microwave background, leading some researchers to speculate that it might represent evidence for exotic physics or even a signature of other universes beyond our own. The discovery of the Eridanus supervoid provided a more conventional explanation for this anomaly. The supervoid is a massive, elongated structure that appears cigar-shaped when viewed from Earth, stretching across hundreds of millions of light-years in the direction of the cold spot. The connection between the void and the temperature anomaly arises from a phenomenon known as the integrated Sachs-Wolf effect, in which photons from the cosmic microwave background lose energy as they pass through large underdense regions of space. As cosmic microwave background photons travel through the expanding Eridanus supervoid, they must climb out of the gravitational potential well created by the void's mass distribution. In a static universe, the energy lost climbing into the void would be exactly balanced by the energy gained falling out of it, leaving the photons unchanged. But because the universe is expanding and the void is growing larger over time, the gravitational potential will become shallower during the photons' journey, causing them to lose a net amount of energy and appear colder when they reach our detectors. The Eridanus supervoid thus serves as a natural explanation for one of the most puzzling features in the cosmic microwave background, demonstrating how large-scale structure can leave its imprint on the radiation from the early universe. This connection between voids and the cosmic microwave background has opened new avenues for studying both the properties of large-scale structure and the fundamental physics of the early universe. Recent observations from the Dark Energy Survey have confirmed the existence of the Eridanus supervoid and provided detailed measurements of its structure and properties. The void appears to be a complex, elongated structure with multiple components, suggesting that it may have formed through the merger of several smaller voids over cosmic time. Its association with the cold spot has made it one of the most intensively studied voids in the universe, providing crucial insights into how large-scale structure affects the cosmic microwave background and how voids evolve over cosmic time. These three great voids, the Boötes Void, the KBC Void, and the Eridanus supervoid, represent different aspects of cosmic emptiness and different challenges to our understanding of the universe. The Boötes Void shows us that vast regions of near emptiness can exist within the cosmic web, challenging our assumptions about cosmic homogeneity. The KBC Void raises the possibility that our own location in the universe may be far from typical, potentially biasing our observations of cosmic expansion and dark energy. The Eridanus supervoid demonstrates how voids can affect the cosmic microwave background radiation, providing a bridge between large-scale structure and the physics of the early universe. Together, these structures remind us that the universe is far stranger and more complex than early astronomers imagined. The cosmic web is not a simple, predictable pattern, but a dynamic, evolving structure full of surprises and anomalies that continue to challenge our understanding of cosmic evolution. In studying these great voids, we are not just mapping the distribution of matter and emptiness in space, but probing the fundamental processes that have shaped the universe from its earliest moments to the present day. To understand how the vast cosmic voids came to dominate the architecture of the universe, we must journey back to the very beginning of time itself, to the first moments after the Big Bang, when the seeds of all future structure were planted in the quantum foam of the primordial cosmos. The story of void formation is ultimately the story of how the universe evolved from a state of near-perfect uniformity to the highly structured cosmos we observe today, a transformation that required the interplay of quantum mechanics, gravity, and the mysterious processes that govern the early universe. In the beginning there was uniformity, the cosmic microwave background radiation, that ancient light that has traveled to us from the surface of last scattering some 380,000 years after the Big Bang, reveals a universe that was remarkably smooth and homogeneous. The temperature variations in this radiation amount to only a few parts in 100,000, indicating that the density of matter and energy in the early universe varied by similarly tiny amounts. Yet, from these minuscule fluctuations, gravity would eventually sculpt the grand architecture of the cosmic web, creating structures that span hundreds of millions of light years. The ultimate origin of these fluctuations lies in the quantum nature of reality itself. During the epoch of cosmic inflation, a period of exponential expansion that occurred in the first tiny fraction of a second after the Big Bang, quantum fluctuations in the inflaton field were stretched to macroscopic scales and frozen into the fabric of space-time. These quantum fluctuations, originally existing on scales smaller than an atomic nucleus, were inflated to sizes comparable to galaxies and galaxy clusters, providing the seeds from which all future cosmic structure would grow. The nature of these primordial fluctuations was fundamentally random, following the statistical laws of quantum mechanics, rather than any predetermined pattern. They created a universe that was almost perfectly smooth, but not quite, with tiny variations in density, scattered throughout space according to the principles of quantum uncertainty. Some regions were slightly denser than average, containing a tiny excess of matter and energy, while others were slightly less dense, representing the first hint of the voids that would eventually dominate the cosmic landscape. As the universe expanded and cooled following the inflationary epoch, these density fluctuations began to evolve under the influence of gravity. The physics governing this evolution is elegantly simple in principle, yet leads to structures of breathtaking complexity. Regions that were slightly denser than average exerted a slightly stronger gravitational pull on their surroundings, attracting additional matter and becoming even denser. Meanwhile, regions that were slightly less dense than average lost matter to their denser neighbors, becoming progressively more empty as cosmic time advanced. This process of gravitational instability operated on all scales simultaneously, from the smallest fluctuations that would eventually become individual galaxies, to the largest fluctuations that would become superclusters and voids. But the growth rate of these fluctuations depended critically on their size and the composition of the universe. Small-scale fluctuations grew quickly, reaching high densities and forming the first stars and galaxies within the first billion years after the Big Bang. Large-scale fluctuations grew more slowly, requiring billions of years to develop into the massive structures we observe today. The formation of cosmic voids was intimately connected to this hierarchical process of structure formation. As matter flowed from underdense regions toward overdense ones, it carved out vast cavities in the cosmic web, creating the voids we observe today. But this process was not simply a matter of matter disappearing from certain regions. Instead, it involved a complex interplay between gravity, pressure, and the expansion of the universe itself. In the early universe, before the formation of the first stars, the cosmos was filled with a hot, ionized gas of hydrogen and helium. This gas was subject to pressure forces that resisted gravitational collapse, creating sound waves that propagated through the primordial plasma at a significant fraction of the speed of light. These acoustic oscillations, known as baryon acoustic oscillations, played a crucial role in shaping the pattern of density fluctuations that would eventually become the cosmic web. The baryon acoustic oscillations created a characteristic scale in the distribution of matter, corresponding to the distance that sound waves could travel in the primordial plasma before the universe cooled enough for atoms to form and the gas to become transparent. This scale, approximately 150 megaparsecs in the present-day universe, shows up as a preferred separation between galaxy clusters and as a typical size for cosmic voids. The voids we observe today thus carry within their structure the imprint of sound waves that propagated through the universe when it was less than 380,000 years old. The transition from the smooth early universe to the structured cosmos of today was not a gradual, uniform process, but rather a series of phase transitions and feedback mechanisms that shaped the evolution of cosmic structure. The formation of the first stars, for example, had profound effects on the surrounding gas, heating it through ultraviolet radiation and enriching it with heavy elements produced by stellar nucleosynthesis. These processes affected the formation of subsequent generations of stars and galaxies, creating a complex web of interactions between small-scale and large-scale structure formation. Dark matter played a particularly crucial role in this process. Unlike ordinary matter, dark matter does not interact electromagnetically and is therefore immune to pressure forces and radiation effects. This allowed dark matter fluctuations to begin growing earlier and faster than ordinary matter fluctuations, creating a scaffolding of gravitational potential wells into which ordinary matter could later fall. The cosmic web we observe today, with its filaments of galaxies and vast intervening voids, is fundamentally a reflection of the underlying dark matter distribution, with ordinary matter tracing the gravitational landscape created by its invisible counterpart. Computer simulations have been essential for understanding this complex process of structure formation. The Millennium simulation, one of the largest and most detailed cosmological simulations ever conducted, followed the evolution of billions of dark matter particles from the early universe to the present day, revealing how the cosmic web emerges from simple initial conditions through the action of gravity alone. These simulations show that void formation is a natural consequence of gravitational instability, with underdense regions becoming progressively more empty as matter flows toward the dense filaments and clusters. The simulations also reveal that void formation is an ongoing process that continues to the present day. Small voids merge to form larger ones, while new voids are carved out of regions that were previously part of filaments or walls. The cosmic web is thus not a static structure, but a dynamic, evolving system that continues to change as the universe ages. The voids we observe today are larger and emptier than they were in the past, and they will continue to grow and merge as the universe expands and ages. One of the most remarkable aspects of void formation is how it connects the smallest scales of physics with the largest scales of cosmic structure. The quantum fluctuations that gave rise to voids originated on scales smaller than an atomic nucleus, yet they eventually created structures hundreds of millions of light years across. This connection between quantum mechanics and cosmology represents one of the most profound insights of modern physics, demonstrating how the fundamental uncertainty principle, that governs the behavior of subatomic particles can shape the architecture of the entire observable universe. The study of void formation has also provided crucial tests of our understanding of fundamental physics. The lambda CDM model, which describes the universe as composed primarily of dark matter and dark energy, makes specific predictions about the number, size, and distribution of voids that should exist at different cosmic epochs. Observations of void populations in galaxy surveys provide direct tests of these predictions, allowing astronomers to constrain the properties of dark matter and dark energy and to test alternative theories of gravity and cosmology. Recent observations have generally confirmed the predictions of the lambda CDM model, but have also revealed some puzzling discrepancies that may point toward new physics. The largest voids, such as the KBC Void, appear to be somewhat larger than the model predicts, raising questions about whether our understanding of structure formation is complete. Some researchers have proposed modifications to the standard model, such as interactions between dark matter and dark energy or alternative theories of gravity, to explain these observations. The formation of cosmic voids also provides insights into the nature of dark energy, the mysterious component that comprises approximately 70% of the universe and is responsible for the accelerated expansion of the cosmos. Voids are particularly sensitive to dark energy because they contain relatively little matter and are therefore dominated by the effects of cosmic expansion. The growth rate of voids over cosmic time provides a direct probe of dark energy's properties, and future observations of void evolution may help determine whether dark energy is truly constant or whether its strength has changed over the history of the universe. As we continue to study the birth of cosmic emptiness, we are not just learning about the formation of voids, but about the fundamental processes that have shaped the universe from its earliest moments to the present day. The story of void formation is ultimately the story of how complexity emerges from simplicity, how the random quantum fluctuations of the early universe gave rise to the magnificent structures we observe today. In understanding how voids formed, we gain insight into the deepest questions of cosmology, the nature of dark matter and dark energy, the validity of our theories of gravity, and the ultimate fate of the universe itself. The cosmic voids thus serve as more than just empty spaces between the galaxies. They are fossil records of the early universe, preserving within their structure the imprint of processes that occurred billions of years ago. They are laboratories for testing our understanding of fundamental physics, providing unique environments where the effects of dark energy and modified gravity theories can be studied. And they are windows into the future, showing us how the universe will continue to evolve as it ages and expands, eventually becoming dominated by ever larger regions of cosmic emptiness. Within the vast expanses of cosmic voids, where darkness stretches across hundreds of millions of light years and matter becomes so sparse that galaxies are separated by distances that dwarf the size of entire galaxy clusters, life persists in forms both familiar and strange. These are not the empty wastelands they might first appear to be, but rather unique cosmic environments that host their own populations of galaxies, their own distributions of dark matter, and their own subtle but profound influences on the evolution of the universe. The galaxies that call cosmic voids home are among the most isolated objects in the universe, existing in a state of cosmic solitude that has shaped their properties in fundamental ways. These void galaxies, as astronomers have come to call them, represent natural experiments in galactic evolution, showing us how cosmic structures develop when freed from the gravitational influences and interactions that dominate galaxy formation in denser regions of space. The first systematic studies of void galaxies revealed that they are markedly different from their counterparts in the filaments and clusters of the cosmic web. They tend to be smaller and less massive, containing fewer stars and exhibiting different patterns of star formation and chemical evolution. This is not surprising when we consider the environment in which they formed. While galaxies in dense regions have access to abundant supplies of gas and dark matter, which they can accrete through gravitational attraction and galactic mergers, void galaxies must make do with the sparse resources available in their underdense surroundings. The isolation of void galaxies has profound effects on their evolutionary histories. In dense regions of the universe, galaxies frequently interact with their neighbors through gravitational encounters, tidal forces, and direct collisions. These interactions can trigger bursts of star formation, strip away gas and stars, and fundamentally alter galactic structure. Void galaxies, by contrast, evolve in relative peace, free from the disruptive influences of close neighbors. This isolation allows them to retain characteristics that might otherwise be erased by environmental effects. One of the most striking features of void galaxies is their tendency toward active star formation. While galaxies in dense environments often exhaust their gas supplies through interactions with neighbors or through the stripping effects of hot intracluster gas, void galaxies can retain their gas reservoirs for much longer periods. This leads to sustained star formation that gives these galaxies a characteristically blue color, indicating the presence of young, hot stars that shine brightly in blue light. The star formation in void galaxies also tends to be more efficient than in typical galaxies, with a higher fraction of available gas being converted into stars. This efficiency may result from the lack of external disturbances that could disrupt the star formation process, allowing gas clouds to collapse and form stars without interference from tidal forces or galactic winds from neighboring systems. The result is a population of galaxies that, despite their small size and isolation, are actively creating new generations of stars. The chemical evolution of void galaxies also differs from that of galaxies in denser environments. Because they experience fewer mergers and interactions, void galaxies tend to have more uniform distributions of heavy elements, with less mixing between different regions of the galaxy. They also tend to have lower overall metallicities, reflecting their smaller masses, and the reduced efficiency of chemical enrichment in low-mass systems. These chemical signatures provide important clues about the formation and evolution of galaxies in different cosmic environments. Perhaps most intriguingly, void galaxies appear to follow different scaling relationships than galaxies in denser regions. The relationships between galactic mass, size, luminosity, and other properties that hold for typical galaxies often break down for void galaxies, suggesting that the environmental effects of cosmic voids extend beyond simple isolation to fundamental changes in the physics of galaxy formation and evolution. But galaxies are not the only inhabitants of cosmic voids. The invisible scaffolding of dark matter that underlies all cosmic structure extends into these seemingly empty regions, creating a subtle web of gravitational influence that shapes the distribution and evolution of both dark and ordinary matter. While the density of dark matter in voids is much lower than in filaments and clusters, it is far from zero, and its gravitational effects play a crucial role in determining the properties and evolution of void regions. Computer simulations reveal that even the emptiest cosmic voids contain extensive networks of dark matter filaments and halos, invisible to our telescopes but detectable through their gravitational effects. These dark matter structures form a kind of skeleton within the voids, providing the gravitational framework upon which the few visible galaxies are built. The dark matter halos in voids tend to be smaller and less massive than those in denser regions, reflecting the lower density environment in which they formed. The distribution of dark matter within voids also shows characteristic patterns that reflect the physics of structure formation in low-density environments. Dark matter halos in voids tend to be more spherical and less concentrated than their counterparts in denser regions, having experienced fewer mergers and less violent evolutionary histories. They also tend to be more isolated, with larger separations between neighboring halos and weaker tidal interactions. The study of dark matter in voids has provided important tests of our understanding of dark matter physics. Different models of dark matter, from the standard cold dark matter paradigm to alternative theories involving warm dark matter or self-interacting dark matter, make different predictions about the structure and distribution of dark matter halos in low-density environments. Observations of void galaxies and their dark matter halos thus provide crucial constraints on the nature of dark matter itself. One of the most remarkable inhabitants of cosmic voids is also one of the most elusive, the neutrino. These ghostly particles, produced in vast numbers by nuclear reactions in stars and by the Big Bang itself, pervade the entire universe, passing through matter with almost no interaction. While neutrinos are present everywhere in the cosmos, their distribution in cosmic voids provides unique opportunities to study their properties and their effects on cosmic structure formation. Unlike ordinary matter and dark matter, which cluster together under the influence of gravity, neutrinos move at speeds close to the speed of light and are therefore largely immune to gravitational clustering on small scales. This means that while galaxies and dark matter halos are concentrated in the filaments and walls of the cosmic web, neutrinos maintain a much more uniform distribution throughout space, including within the cosmic voids. The uniform distribution of neutrinos has important consequences for the evolution of cosmic voids. While the gravitational effects of individual neutrinos are negligible, the collective gravitational influence of all the neutrinos within a void can be significant, affecting the rate at which the void expands and evolves over cosmic time. Voids containing more neutrinos expand more slowly than those with fewer neutrinos, providing a potential method for measuring the total mass of neutrinos in the universe. This connection between neutrino mass and void evolution has made cosmic voids powerful tools for neutrino physics. By comparing the observed sizes and expansion rates of voids at different cosmic epochs, astronomers can constrain the sum of neutrino masses with a precision that rivals or exceeds that of laboratory experiments. This represents a remarkable convergence between cosmology and particle physics, demonstrating how the largest structures in the universe can provide insights into the properties of the smallest particles. The study of neutrinos and voids has also revealed unexpected connections between cosmic structure formation and fundamental physics. The presence of massive neutrinos affects the growth of cosmic structure on large scales, suppressing the formation of small-scale structure while having less effect on larger scales. This scale-dependent suppression leaves characteristic signatures in the distribution of galaxies and voids that can be detected through careful statistical analysis of large galaxy surveys. Recent observations have begun to detect these neutrino signatures in cosmic structure, providing the first direct cosmological evidence for neutrino mass. The Sloan Digital Sky Survey and other large-scale surveys have measured the distribution of galaxies and voids with sufficient precision to detect the subtle effects of neutrino mass on structure formation, opening a new window into neutrino physics through cosmological observations. The inhabitants of cosmic voids also include more exotic forms of matter and energy. Dark energy, the mysterious component that drives the accelerated expansion of the universe, is thought to be uniformly distributed throughout space, but its effects are most pronounced in regions where ordinary matter and dark matter are sparse. Cosmic voids, with their low matter densities, are therefore dominated by dark energy, making them natural laboratories for studying this enigmatic component of the cosmos. The dominance of dark energy in voids has important consequences for their evolution and properties. While regions of high matter density are slowed in their expansion by gravitational attraction, voids expand more rapidly due to the repulsive effects of dark energy. This differential expansion contributes to the growth of cosmic structure, with voids becoming larger and emptier over time, while dense regions become more concentrated. The study of void evolution thus provides direct probes of dark energy properties. By measuring how the sizes and shapes of voids change over cosmic time, astronomers can constrain the equation of state of dark energy and test whether its properties have remained constant throughout cosmic history. Future surveys that map the three-dimensional distribution of galaxies over large volumes and long cosmic epochs will provide unprecedented opportunities to study dark energy through its effects on void evolution. Even within the sparse environment of cosmic voids, the interplay between different components of the cosmic inventory creates complex and fascinating phenomena. The gravitational effects of dark matter halos influence the formation and evolution of void galaxies, while the presence of neutrinos affects the rate of void expansion. Dark energy drives the overall evolution of void structure, while the feedback effects of star formation and galactic winds from void galaxies can influence the distribution of gas and the formation of subsequent generations of stars. The inhabitants of cosmic emptiness thus form a complex ecosystem, with each component influencing the others in subtle but important ways. The study of this ecosystem provides insights not only into the nature of cosmic voids themselves, but into the fundamental physics that governs the behavior of matter, energy, and space-time on the largest scales. In the sparse populations of void galaxies, in the invisible networks of dark matter, in the uniform sea of neutrinos, and in the pervasive influence of dark energy, we find a microcosm of the universe itself, revealing the intricate connections between the largest and smallest scales of physical reality. As we continue to explore these cosmic wildernesses, we are reminded that even in the emptiest regions of space, the universe remains rich with structure, complexity, and mystery. The inhabitants of the voids may be sparse and widely separated, but they are no less important for understanding the cosmos than the dense clusters and bright galaxies that dominate our attention. In their isolation and uniqueness, they provide irreplaceable insights into the processes that have shaped the universe from its earliest moments to the present day. In the grand theater of the cosmos, cosmic voids serve as nature's most pristine laboratories, offering unique environments where the fundamental laws of physics can be tested under conditions impossible to replicate on Earth or even in the dense regions of the universe. These vast expanses of near emptiness provide cosmologists with unprecedented opportunities to probe the deepest mysteries of existence, the nature of gravity on cosmic scales, the properties of dark energy, and the validity of our most cherished theories about the structure of reality itself. The story of how cosmic voids became crucial testing grounds for fundamental physics begins with one of the most profound questions in modern cosmology. Does Einstein's theory of general relativity, which has passed every test in the solar system and in the vicinity of compact objects like neutron stars and black holes, continue to hold true on the largest scales of the universe? This question is not merely academic, for if gravity behaves differently on cosmic scales than it does locally, it could fundamentally alter our understanding of dark matter, dark energy, and the evolution of the universe itself. The challenge of testing general relativity on cosmic scales lies in the complexity of the environments where most cosmic structure exists. In the dense filaments and clusters of the cosmic web, multiple gravitational influences compete and interact, making it difficult to isolate the effects of gravity itself from the complex dynamics of gas, stars, and dark matter. Cosmic voids, by contrast, offer relatively simple environments where the effects of gravity can be studied in relative isolation, free from the complications that plague observations in denser regions. The breakthrough in using voids to test general relativity came from the realization that the walls of matter surrounding cosmic voids provide a natural laboratory for studying gravitational physics. As a void expands due to the overall expansion of the universe and the influence of dark energy, it pushes against the surrounding walls of galaxies and dark matter, causing these walls to thicken over time as matter accumulates at the void boundaries. The rate at which this thickening occurs depends critically on the strength and behavior of gravity on large scales. In 2020, a team of researchers led by Nico Hamaus, Alice Pisani, and Benjamin Wandelt published a landmark study that used this wall thickening effect to test general relativity on scales of hundreds of millions of light years. Their analysis of cosmic voids in galaxy survey data revealed that the observed thickening of void walls matched the predictions of Einstein's theory with remarkable precision, providing the first direct test of general relativity on truly cosmic scales. The elegance of this test lies in its conceptual simplicity. Imagine a cosmic void as the expanding bubble in the cosmic web, pushing outward against the surrounding matter as it grows. The rate at which matter accumulates at the bubble's edge depends on how gravity behaves. If gravity is stronger than Einstein predicted, matter would accumulate faster, creating thicker walls. If gravity is weaker, the walls would remain thinner. By measuring the actual thickness of void walls and comparing it to theoretical predictions, astronomers can directly test whether general relativity accurately describes gravity on cosmic scales. The implications of this test extend far beyond academic curiosity. Many alternative theories of gravity have been proposed to explain the observed acceleration of cosmic expansion without invoking dark energy, suggesting instead that gravity itself behaves differently on large scales than Einstein's theory predicts. These modified gravity theories make specific predictions about how cosmic voids should evolve and how their walls should thicken over time. The observation that void wall evolution matches Einstein's predictions places strong constraints on these alternative theories, supporting the standard model of cosmology while ruling out many proposed modifications to gravity. But the utility of cosmic voids as laboratories for fundamental physics extends far beyond tests of gravity. These vast underdense regions have emerged as some of the most powerful tools available for studying dark energy, the mysterious component that comprises approximately 70% of the universe and drives its accelerated expansion. The reason voids are so sensitive to dark energy lies in their unique composition, with relatively little ordinary matter or dark matter. To provide gravitational attraction, voids are dominated by the repulsive effects of dark energy. This dominance of dark energy in cosmic voids makes them exquisitely sensitive probes of dark energy's properties. As dark energy drives the accelerated expansion of the universe, it affects the growth rate of cosmic voids in ways that depend on the specific nature of dark energy itself. If dark energy is truly Einstein's cosmological constant, a form of energy inherent in empty space itself, then voids should expand at a particular rate that can be calculated from first principles. If dark energy is something else, a dynamic field that changes over time or varies from place to place, then void expansion should follow different patterns. The study of void evolution over cosmic time thus provides a direct window into the nature of dark energy. By comparing the sizes and shapes of voids at different cosmic epochs, astronomers can trace how dark energy has influenced cosmic expansion throughout the history of the universe. This approach has already yielded important constraints on dark energy properties, confirming that its effects are consistent with a cosmological constant, while ruling out many alternative models. Future observations promise even more precise tests of dark energy through void studies. The next generation of galaxy surveys, including the Dark Energy Spectroscopic Instrument and the Euclid Space Telescope, will map the three-dimensional distribution of galaxies over unprecedented volumes and with extraordinary precision. These surveys will catalog hundreds of thousands of cosmic voids, providing the statistical power needed to detect subtle variations in dark energy properties and to test whether dark energy has remained constant throughout cosmic history. The power of cosmic voids as laboratories for fundamental physics extends to some of the most exotic and speculative ideas in modern cosmology. Modified gravity theories, which propose alternatives to both general relativity and dark energy, make specific predictions about void properties that can be tested through observation. Some theories suggest that gravity becomes weaker on very large scales, leading to faster void expansion. Others propose that gravity is modified in low-density environments, affecting the internal structure of voids themselves. Cosmic voids also provide unique opportunities to study the quantum nature of space-time itself. Some theories of quantum gravity suggest that the fabric of space-time has a discrete, granular structure on the smallest scales, similar to the way matter is composed of atoms. While these quantum effects are far too small to detect directly, they might leave subtle signatures in the statistical properties of cosmic structure that could be detectable in large surveys of cosmic voids. The study of cosmic voids has also opened new avenues for exploring the connection between quantum mechanics and cosmology. The quantum fluctuations that gave rise to cosmic structure during inflation left their imprint not only in the cosmic microwave background radiation, but also in the statistical properties of cosmic voids. By analyzing the shapes, sizes, and spatial distribution of voids, astronomers can probe the quantum processes that operated during the first moments of cosmic history. One of the most intriguing applications of void studies involves the search for evidence of cosmic strings, hypothetical one-dimensional defects in space-time that might have formed during phase transitions in the early universe. These exotic objects, if they exist, would leave characteristic signatures in the distribution of cosmic structure, including distinctive patterns in the shapes and alignments of cosmic voids. While no definitive evidence for cosmic strings has been found, ongoing surveys continue to search for their signatures in void catalogs. The use of cosmic voids as laboratories for fundamental physics has also revealed unexpected connections between cosmology and particle physics. The masses of neutrinos, for example, can be constrained through their effects on void evolution, as we discussed in the previous chapter. But voids are sensitive to other particle physics parameters as well, including the number of neutrino species, the properties of dark matter particles, and even the existence of additional spatial dimensions beyond the three we experience directly. Some theories of particle physics predict the existence of axions, hypothetical particles that could comprise a significant fraction of dark matter. These particles would have subtle but detectable effects on the formation and evolution of cosmic structure, including characteristic signatures in the properties of cosmic voids. Similarly, theories that propose extraspatial dimensions make specific predictions about how gravity should behave on different scales, predictions that can be tested through careful analysis of void properties. The emerging field of void cosmology has also begun to explore the possibility that cosmic voids could serve as laboratories for studying the fundamental nature of time itself. Some theories suggest that time might flow differently in regions of different matter density, with time passing slightly faster in the low-density environment of cosmic voids compared to the dense regions of galaxy clusters. While these effects would be extraordinarily small, they might be detectable through precise measurements of void evolution over cosmic time. Perhaps most remarkably, cosmic voids are beginning to provide insights into one of the deepest questions in physics, the nature of the vacuum itself. In quantum field theory, even empty space is filled with quantum fluctuations, virtual particles that pop in and out of existence on timescales too short to observe directly. The properties of this quantum vacuum might affect the evolution of cosmic voids in subtle but measurable ways, providing a bridge between quantum mechanics and cosmology that could illuminate the fundamental nature of reality. The study of cosmic voids as laboratories for fundamental physics represents a remarkable convergence of observational astronomy, theoretical physics, and computational cosmology. It demonstrates how the largest structures in the universe can provide insights into the smallest scales of physical reality, and how the emptiest regions of space can reveal the deepest truths about the nature of existence itself. As we continue to develop more sophisticated techniques for studying cosmic voids, and as new generations of surveys provide ever more detailed maps of cosmic structure, these vast regions of emptiness will undoubtedly continue to surprise us with new insights into the fundamental laws of physics. In the cosmic silence of the voids, we are learning to hear the whispers of quantum mechanics, the echoes of general relativity, and the subtle signatures of dark energy that permeate the fabric of space-time itself. The quest to map the cosmic voids has driven some of the most ambitious technological achievements in the history of astronomy, pushing the boundaries of what is possible in terms of data collection, processing, and analysis. The story of void detection is ultimately the story of how astronomers learn to see in 3 dimensions, transforming the flat, 2-dimensional view of the night sky that had constrained human understanding for millennia into a rich 3-dimensional map of cosmic structure that reveals the true architecture of the universe. The journey began in the early 20th century with the pioneering work of astronomers like Vesto Slipher and Edwin Hubble, who first measured the redshifts of galaxies and discovered that the universe is expanding. But these early observations, groundbreaking as they were, provided only hints of the 3-dimensional structure of the cosmos. Astronomers could measure the distances to individual galaxies, but they lacked the technology and techniques needed to map large volumes of space systematically. The breakthrough came with the development of large-scale redshift surveys in the 1970s and 1980s. The principle behind these surveys is elegantly simple. By measuring the redshift of light from thousands or millions of galaxies, astronomers can determine not only the direction to each galaxy as seen from Earth, but also its distance allowing them to construct three-dimensional maps of cosmic structure. The redshift of a galaxy's light, caused by the expansion of the universe, serves as a cosmic yardstick, with more distant galaxies showing larger redshifts due to the greater expansion that has occurred during the longer time their light has traveled to reach us. The first major redshift survey to reveal the existence of cosmic voids was the Center for Astrophysics Redshift Survey, conducted in the late 1970s and early 1980s. Using relatively modest telescopes and early electronic detectors, astronomers painstakingly measured the redshifts of several thousand galaxies in a narrow slice of sky. When they plotted these galaxies in three-dimensional space, the results were revolutionary. Instead of a random distribution, they found a complex pattern of filaments and walls surrounding vast empty regions. The most famous result from this survey was the discovery of what became known as the Great Wall, a vast sheet of galaxies stretching across hundreds of millions of light years. But equally important was the recognition of the voids, the empty regions between the walls and filaments that occupy most of the volume of the surveyed region. These early surveys provided the first clear evidence that the universe has a foam-like structure on the largest scales, with matter concentrated in thin walls and filaments surrounding enormous bubbles of near emptiness. The technology of redshift measurement has evolved dramatically since these pioneering surveys. Early observations required astronomers to position a spectrograph at the focus of a telescope and collect light from individual galaxies one at a time, a process that could take hours for each object. Modern surveys employ sophisticated multi-object spectrographs that can simultaneously measure the redshifts of hundreds of galaxies, dramatically increasing the efficiency of data collection. The development of charge-coupled devices, or CCDs, revolutionized astronomical imaging and spectroscopy, providing detectors that were far more sensitive and stable than the photographic plates and photomultiplier tubes used in earlier surveys. These electronic detectors could record the faint light from distant galaxies with unprecedented precision, allowing astronomers to measure redshifts for much fainter and more distant objects than had previously been possible. The Sloan Digital Sky Survey, which began operations in 2000, represents a quantum leap in the scale and precision of redshift surveys. Using a dedicated 2.5-meter telescope equipped with advanced CCD cameras and spectrographs, SDSS has measured redshifts for millions of galaxies over a significant fraction of the sky. The survey's systematic approach, covering large contiguous areas of sky to uniform depth and precision, has provided the most comprehensive three-dimensional map of cosmic structure ever created. The SDSS data have revolutionized our understanding of cosmic voids, providing catalogs containing thousands of individual voids with well-measured properties. These catalogs have enabled statistical studies of void populations that were impossible with earlier, smaller surveys. Astronomers can now study how void properties correlate with environment, how voids have evolved over cosmic time, and how they relate to other aspects of cosmic structure formation. The success of SDSS has inspired a new generation of even more ambitious surveys. The Dark Energy Survey, conducted using a 4-meter telescope in Chile, has mapped hundreds of millions of galaxies over a large area of the southern sky, providing unprecedented precision in measurements of cosmic structure. The survey's primary goal is to study dark energy through multiple complementary techniques, including the statistical analysis of cosmic voids. Future surveys promise even more dramatic advances in our ability to map cosmic voids. The Dark Energy Spectroscopic Instrument, or DC, began operations in 2021 with the goal of measuring redshifts for tens of millions of galaxies over the next 5 years. DESI's advanced spectrograph can simultaneously observe 5,000 galaxies, allowing it to map cosmic structure with unprecedented speed and precision. The Euclid Space Telescope, launched by the European Space Agency, will provide complementary observations from space, free from the distorting effects of Earth's atmosphere. Euclid will measure the shapes and redshifts of billions of galaxies, providing 3-dimensional maps of cosmic structure that extend to much greater distances than ground-based surveys can achieve. The Roman Space Telescope, currently under development by NASA, will push these capabilities even further, using advanced infrared detectors to study the most distant galaxies and map cosmic structure during earlier epochs of cosmic history. These future surveys will provide time-lapse movies of cosmic evolution, showing how voids and other large-scale structures have changed over billions of years. The analysis of data from these surveys requires sophisticated computational techniques that push the boundaries of data processing and statistical analysis. Modern void-finding algorithms must sift through catalogs containing millions of galaxies to identify the 3-dimensional regions where galaxy density drops below a specified threshold. This process involves complex geometric calculations and statistical tests that require substantial computational resources. The development of machine learning techniques has begun to revolutionize void detection and analysis. Neural networks and other artificial intelligence algorithms can identify voids in galaxy catalogs with greater speed and accuracy than traditional methods, while also discovering subtle patterns and correlations that might be missed by conventional analysis techniques. These AI-powered approaches are particularly valuable for analyzing the massive datasets produced by modern surveys, where traditional methods might be overwhelmed by the sheer volume of data. One of the most exciting developments in void research has been the creation of virtual reality visualizations that allow researchers and the public to explore cosmic voids in 3 dimensions. Alice Pisani's collaboration with computer science student Bonnie Yue Wang produced a VR experience that lets users walk through actual cosmic voids, experiencing the vast emptiness and sparse galaxy populations that characterize these regions. These visualizations provide intuitive understanding of void structure that is difficult to achieve through traditional 2-dimensional plots and statistical analyses. The VR experience of cosmic voids reveals aspects of their structure that are not immediately apparent from conventional representations. Users can appreciate the true 3-dimensional nature of voids, seeing how they connect to form larger structures and how the few galaxies within them are distributed. The experience of standing within a cosmic void surrounded by vast emptiness, with only occasional distant galaxies visible on the horizon, provides a visceral understanding of the scale and nature of these structures. These visualization techniques are not merely educational tools, but also research instruments that can reveal new insights into void structure and evolution. By exploring voids in virtual reality, researchers can identify patterns and relationships that might not be apparent in traditional statistical analyses. The human visual system evolved to recognize patterns in three-dimensional space, can sometimes detect structures and correlations that are missed by automated algorithms. The technology of void detection continues to evolve rapidly, driven by advances in detector technology, computational power, and analysis techniques. Future surveys will employ even more sophisticated instruments, including adaptive optics systems that correct for atmospheric turbulence, advanced spectrographs that can measure redshifts for fainter galaxies, and space-based telescopes that can observe at wavelengths impossible from the ground. The data processing challenges posed by these future surveys are enormous. The Large Synoptic Survey Telescope, now known as the Vera C. Rubin Observatory, will generate tens of terabytes of data each night, requiring real-time processing systems that can identify and catalog cosmic structures as the data are collected. The analysis of such massive datasets will require new computational approaches, including distributed computing systems and advanced machine learning algorithms. The study of cosmic voids is also benefiting from advances in computational cosmology, particularly the development of ever more sophisticated numerical simulations of cosmic structure formation. These simulations, run on the world's most powerful supercomputers, can follow the evolution of billions of particles from the early universe to the present day, providing detailed predictions for the properties and evolution of cosmic voids that can be compared with observations. The Millennium simulation and its successors have provided crucial insights into void formation and evolution, revealing how these structures emerge from the gravitational instability of small density fluctuations in the early universe. More recent simulations, such as the Illustrious and Eagle projects, include the effects of gas dynamics, star formation, and feedback from supernovae and black holes, providing more realistic predictions for the properties of void galaxies and their environments. The combination of increasingly powerful observations and simulations is driving rapid progress in our understanding of cosmic voids. Each new survey provides more detailed maps of void structure, while each new simulation provides more sophisticated predictions for how these structures should behave. The interplay between observation and theory continues to refine our understanding of these cosmic deserts and their role in the larger story of cosmic evolution. As we look toward the future, the technology of void detection promises even more remarkable discoveries. The next generation of surveys will map cosmic structure with unprecedented precision over vast volumes of space and time, providing new insights into the nature of dark matter, dark energy, and the fundamental physics that governs the evolution of the universe. In the vast emptiness of cosmic voids, revealed through humanity's most sophisticated technological achievements, we continue to find new windows into the deepest mysteries of existence. As we stand at the threshold between scientific understanding and philosophical contemplation, cosmic voids invite us to grapple with some of the most profound questions that have occupied human thought since the dawn of consciousness. What does it mean for something to be empty? How do we comprehend nothingness on scales that dwarf human experience? And what does our potential residence within a cosmic void tell us about our place in the grand scheme of existence? The philosophical implications of cosmic voids extend far beyond their scientific significance, touching on fundamental questions about the nature of reality, existence, and meaning that have puzzled philosophers for millennia. In confronting the vast emptiness of cosmic voids, we are forced to reconsider our most basic assumptions about space, time, and the relationship between something and nothing. The concept of nothingness has been central to philosophical inquiry across cultures and throughout history. Ancient Greek philosophers debated whether true emptiness could exist, with some arguing that nature bores a vacuum and others proposing that void space was necessary for motion and change to occur. Aristotle famously argued against the existence of void space, claiming that it would lead to logical contradictions, while the atomists, like Democritus, insisted that empty space was essential for the movement of atoms that comprised all matter. Buddhist philosophy has long grappled with the concept of emptiness or shunyata, though in a sense quite different from the physical emptiness of cosmic voids. In Buddhist thought, emptiness refers to the lack of inherent, independent existence in all phenomena, suggesting that all things arise through interdependence and lack fixed, permanent essence. This philosophical emptiness paradoxically becomes a source of fullness as it allows for the infinite potential of existence to manifest. The discovery of cosmic voids adds a new dimension to these ancient philosophical questions. Here we have regions of space that are not merely empty in the sense of lacking particular objects, but are empty on scales so vast that they challenge our ability to comprehend emptiness itself. A cosmic void is not like an empty room, which still contains air, light, and the potential for occupation. It is more like an empty universe, a region where the very fabric of existence becomes so sparse that the normal rules of cosmic evolution are suspended. Yet even this cosmic emptiness is not absolute. As we have seen, cosmic voids contain dark matter, neutrinos, and the occasional lonely galaxy. They are permeated by dark energy and crossed by the faint light of distant stars. In this sense, they remind us that true nothingness may be impossible to achieve, that even in the emptiest regions of space, existence persists in subtle forms. The realization that we may ourselves reside within a cosmic void adds a deeply personal dimension to these philosophical reflections. If the KBC Void truly encompasses our local group and much of our cosmic neighborhood, then we are not observers looking out at cosmic emptiness from a position of cosmic normalcy, but inhabitants of that emptiness ourselves. This possibility fundamentally alters our perspective on our place in the universe. Throughout human history, each major scientific discovery has required us to reassess our cosmic significance. Copernicus displaced Earth from the center of the universe, showing that we orbit an ordinary star. Hubble revealed that our galaxy is one of billions in an expanding universe. The discovery of exoplanets has suggested that planetary systems are common throughout the cosmos. Each of these revelations has been seen as diminishing human importance, making us seem ever smaller and more insignificant in the cosmic scheme. But the possibility that we live within a cosmic void presents a different kind of cosmic displacement. Rather than making us seem smaller, it makes our entire cosmic neighborhood seem emptier, more isolated, more unusual. If we reside in a region where matter density is significantly below the cosmic average, then our observations of the universe may be biased by our unusual location. The cosmic acceleration we attribute to dark energy, the distribution of galaxies we observe, even the rate of cosmic expansion we measure, might all be influenced by our residence in a cosmic desert. This possibility raises profound questions about the nature of scientific observation and the assumptions that underlie our understanding of the universe. The Copernican principle, which assumes that we occupy a typical location in the universe, has been fundamental to the development of modern cosmology. If we live in a cosmic void, this principle may need to be reconsidered, with implications that extend throughout our understanding of cosmic evolution and fundamental physics. Yet, there is also something deeply poetic about the possibility of residing in cosmic emptiness. It suggests that consciousness, life, and intelligence have emerged not in the dense, active regions of the cosmic web, but in the quiet, sparse regions where the universe approaches its most minimal state. There is a kind of cosmic irony in the idea that the most complex structures we know of, living organisms and thinking beings, have arisen in regions where the universe is at its simplest and most empty. This irony connects to deeper questions about the relationship between complexity and simplicity, between fullness and emptiness, that have long fascinated philosophers and mystics. In many spiritual traditions, the highest states of consciousness are associated with emptiness, silence, and the dissolution of ordinary distinctions. The cosmic voids, in their vast silence and minimal structure, might be seen as the universe's own meditation on emptiness, regions where the cosmos approaches a state of pure potential. The aesthetic dimension of cosmic voids also deserves contemplation. There is a stark beauty in these vast empty regions, a kind of cosmic minimalism that reduces existence to its most essential elements, like the empty spaces in a Japanese garden or the silence between notes in a musical composition. Cosmic voids derive their power not from what they contain, but from what they lack. They are negative spaces that define and give meaning to the positive spaces of galaxies and stars. This aesthetic of emptiness has found expression in various forms of human art and culture. The concept of MR in Japanese aesthetics refers to the pregnant pause, the meaningful emptiness that gives shape and significance to what surrounds it. In Western art, the use of negative space has been recognized as essential to composition and meaning. Cosmic voids represent the ultimate expression of this aesthetic principle, negative spaces so vast that they shape the structure of the entire observable universe. The contemplation of cosmic voids also invites reflection on the nature of time and duration. Within these vast empty regions, Change occurs on timescales that dwarf human experience. The few galaxies within voids evolve in isolation over billions of years, their light taken hundreds of millions of years to cross from one side of the void to the other. In this context, human life, human civilization, even the entire history of our species, becomes a brief flicker in the cosmic silence. Yet this perspective on cosmic time need not be diminishing or depressing. Instead, it can be liberating, freeing us from the urgency and anxiety that often characterize human experience. In the vast patience of cosmic voids, we might find a model for a different kind of existence, one that operates on longer timescales and finds meaning in persistence rather than change. The study of cosmic voids also raises questions about the nature of scientific knowledge itself. How do we come to understand something that is defined by absence rather than presence? How do we map emptiness, measure nothingness, or catalog the void? The scientific study of cosmic voids requires us to develop new ways of thinking about space and structure, to find meaning in statistical absences and significance in what is not there. This challenge connects to broader questions in philosophy of science, about the nature of scientific explanation and understanding. Traditional scientific explanation often focuses on identifying causes, mechanisms, and positive relationships between phenomena. But the study of cosmic voids requires a different approach, one that finds explanatory power in the absence of mechanisms, in the lack of relationships, in the minimal nature of structure itself. The philosophical implications of cosmic voids extend to questions about consciousness and meaning as well. If consciousness has emerged within cosmic voids, in regions where the universe is at its most minimal, what does this tell us about the relationship between mind and cosmos? Are we, as conscious beings, the universe's way of contemplating its own emptiness? Do we represent the cosmos becoming aware of its own vast silences? These questions connect to ancient philosophical problems about the relationship between mind and matter, consciousness and cosmos. The emergence of awareness within cosmic emptiness suggests a kind of cosmic irony, where the universe's most complex achievements arise in its simplest regions. This paradox might point toward deeper truths about the nature of existence itself, suggesting that complexity and simplicity, fullness and emptiness, are more intimately connected than we might initially suppose. As we continue to study and contemplate cosmic voids, we are engaged in more than scientific research. We are participating in humanity's ongoing dialogue with the cosmos, seeking to understand not just the physical structure of the universe, but our place within it and the meaning of our existence. The vast emptiness of cosmic voids serves as a mirror for our own contemplation, reflecting back our deepest questions about existence, meaning, and the nature of reality itself. In the silence of cosmic voids, we find not just empty space, but an invitation to philosophical reflection. These vast regions of near-nothingness challenge us to think more deeply about what it means to exist, to be conscious, to find meaning in a universe that is predominantly empty. They remind us that even in emptiness there is structure, even in silence there is significance, even in the void there is the potential for wonder, understanding, and awe. As our journey through the loneliest places in the universe draws toward its close, we find ourselves standing at the edge of cosmic understanding, gazing into a future where the vast emptiness we have explored will play an ever more dominant role in the story of existence itself. The cosmic voids, which began as curious anomalies in early galaxy surveys, have revealed themselves to be fundamental features of cosmic architecture, windows into the deepest physics of reality, and harbingers of the universe's ultimate destiny. The future of void research promises discoveries that will further revolutionize our understanding of the cosmos. In the coming decades, astronomical surveys of unprecedented scale and precision will catalog hundreds of thousands of cosmic voids, providing the statistical power needed to detect subtle effects that remain hidden in current datasets. The Dark Energy Spectroscopic Instrument, the Euclid Space Telescope, and the Vera C. Rubin Observatory will work together to create three-dimensional maps of cosmic structure that extend across billions of light years and back through billions of years of cosmic history. These future observations will allow astronomers to watch cosmic voids evolve in real time, comparing their properties at different cosmic epochs to trace how they have grown and changed as the universe has aged. This cosmic archaeology will provide crucial tests of our understanding of dark energy, dark matter, and the fundamental forces that govern cosmic evolution. We will be able to determine whether dark energy has remained constant throughout cosmic history, or whether its properties have evolved, potentially revealing new physics beyond the standard model of cosmology. The next generation of void studies will also push into entirely new regimes of cosmic structure. Future surveys will detect voids at much greater distances than current observations, allowing us to study how these structures formed and evolved during the early epochs of cosmic history, when the universe was denser and more active. We may discover that the properties of voids have changed dramatically over cosmic time, providing new insights into the processes that shaped the cosmic web. Machine learning and artificial intelligence will play increasingly important roles in void research, enabling the analysis of datasets so large and complex that traditional methods would be overwhelmed. Neural networks trained on cosmological simulations will be able to extract subtle patterns and correlations from void catalogs, potentially discovering new relationships between void properties and fundamental physics that human researchers might miss. The study of cosmic voids will also benefit from advances in gravitational wave astronomy. As detectors become more sensitive and new facilities come online, we may be able to detect the gravitational wave signatures of cosmic structure formation, including the effects of void evolution on the propagation of gravitational waves across cosmic distances. This will provide an entirely new window into the dynamics of cosmic voids and their role in shaping space-time itself. But perhaps the most profound implications of void research lie not in the discoveries yet to be made, but in what these structures tell us about the ultimate fate of the universe itself. As we have seen, cosmic voids are expanding faster than the denser regions of the cosmic web, driven by the repulsive effects of dark energy. This differential expansion means that voids will continue to grow larger and emptier as the universe ages, eventually coming to dominate the cosmic landscape even more completely than they do today. Current models of cosmic evolution suggest that we are living through a relatively brief epoch in cosmic history when stars still shine brightly and galaxies still form new generations of stellar systems. In the far future, as the universe continues to expand and age, star formation will gradually cease as the supply of gas needed to create new stars is exhausted. The existing stars will burn out one by one, leaving behind white dwarfs, neutron stars, and black holes as the only remnants of the once brilliant cosmic web. In this far future universe, cosmic voids will expand to encompass ever larger fractions of space, with the remaining matter concentrated into increasingly isolated islands separated by vast gulfs of emptiness. The cosmic web, which today spans the observable universe with its intricate pattern of filaments and walls, will gradually dissolve as the expansion of space carries its components ever further apart. On even longer timescales, measured in trillions upon trillions of years, even the black holes that represent the final evolutionary state of massive stars will evaporate through Hawking radiation, leaving behind a universe composed almost entirely of elementary particles scattered across vast distances. In this ultimate future, the cosmic voids will have won their patient battle with structure, expanding until they encompass virtually all of space. This vision of cosmic evolution, sometimes called the heat death of the universe, might seem bleak and depressing, suggesting that all the complexity and beauty we observe today is destined to fade into cold, empty darkness. But there is another way to view this cosmic destiny, one that finds meaning and even beauty in the universe's return to simplicity and silence. The cosmic voids, in their vast patience and minimal structure, might be seen as the universe's natural state, the condition toward which all cosmic evolution ultimately tends. The brief epoch of stars and galaxies, of planets and life, of consciousness and civilization, represents a temporary departure from this fundamental emptiness, a fleeting moment of complexity in an otherwise simple cosmos. From this perspective, we are living during a remarkable period in cosmic history when the universe has temporarily organized itself into structures complex enough to give rise to consciousness and understanding. The fact that we exist at all, that we can contemplate cosmic voids and ponder their implications, represents a kind of cosmic miracle, an unlikely flowering of complexity in a universe that tends towards simplicity. The study of cosmic voids thus provides a unique perspective on the meaning and significance of existence itself. In contemplating these vast empty regions, we are forced to confront fundamental questions about the nature of reality, the purpose of existence, and our place in the cosmic scheme. The voids remind us that the universe is predominantly empty, that structure and complexity are rare and precious, and that consciousness represents one of the most remarkable achievements in the history of the cosmos. Yet the voids also teach us about patience, persistence, and the power of gradual change. These structures have evolved over billions of years, growing slowly and steadily as the universe has expanded and aged. They remind us that the most profound transformations often occur on timescales that dwarf human experience, and that understanding the cosmos requires us to think beyond the brief span of individual lives or even entire civilizations. The loneliest places in the universe thus become teachers, offering lessons about time, space, existence, and meaning that we could learn nowhere else. In their vast silence, we find not emptiness but fullness, not absence but presence, not meaninglessness but profound significance. They show us that even nothingness has structure, that even emptiness has beauty, and that even silence has something important to say. As we conclude our journey through the cosmic voids, we carry with us a new appreciation for the complexity and wonder of the universe, even in its emptiest regions. We have seen how these vast spaces between the galaxies are not merely empty wastelands, but active participants in cosmic evolution, laboratories for fundamental physics, and windows into the deepest mysteries of existence. The cosmic voids remind us that the universe is far stranger and more wonderful than our everyday experience might suggest. They challenge our assumptions about space and time, matter and energy, existence and nothingness. They invite us to think more deeply about our place in the cosmos and the meaning of our brief moment of consciousness in the vast sweep of cosmic history. In the end, the loneliest places in the universe teach us that we are not alone. Even in the emptiest regions of space, we find connections to the fundamental forces and processes that govern all of existence. We are part of the cosmic web, participants in the grand story of cosmic evolution, temporary arrangements of matter and energy that have somehow become aware of themselves and their cosmic context. The eternal silence of the cosmic voids is not the silence of death or meaninglessness, but the silence of patience, of potential, of the deep peace that underlies all existence. In this silence, we find not isolation but connection, not emptiness but fullness, not an ending but a beginning. For in learning to listen to the cosmic silence, we learn to hear the subtle music of existence itself, the quiet symphony of space and time, matter and energy, consciousness and cosmos that plays eternally in the vast concert hall of the universe. The journey to the loneliest places in the universe thus becomes a journey to the heart of existence itself, a pilgrimage to the sources of meaning and wonder that make consciousness possible and life worthwhile. In the cosmic voids, we find not just empty space, but the very foundations of reality, the stage upon which the drama of existence unfolds, and the silent witness to all that has been, is, and ever will be.